So today we'll talk about a model for financial systemic risk, which we've been developing together with Professor Stefano Marmi and Matteo Tanzi. So what is systemic risk in finance? This refers to the event in which several banks may fail in a relatively short time window, thus compromising the functioning of the whole system. And there are several mechanisms for which this may happen. One of these is due to the fact that several banks may invest in the same assets. So should one of them fail, go down in price, then all of the other banks which are investing in the same assets may suffer a loss in their portfolio simultaneously. And this is, of course, just one of the mechanisms that may happen, but this is the one we will focus in this talk. So to give an idea of the importance of the phenomenon, this plot shows the number that, only in the US in the last 20 years there have been almost 600 failures for a total assets, for a total loss of assets of several billions of dollars. So, and this table shows that the first banks in the world have assets of the order of several thousands of billions of dollars. So should one of them fail, the impact on the real economy of the world is quite relevant. So to model systemic risk, this kind of systemic risk, it turns out that it is useful to start from this quantity, which is called the financial leverage. This is a real number which is associated with each bank, and it is defined as the ratio between the assets of the bank and the equity of the bank. So a larger, a leverage greater than 1 means that the bank is borrowing money to invest. So the idea is that the more money the bank invests, the larger the profits it will make. So it is naturally led to borrow money to invest them. And of course, this means an amplification of gains if things go well, but may also mean an amplification of losses if things go bad. And indeed, there are some regulations on the maximum value that this quantity can attain. This, in practice, results in a maximum leverage value for the leverage which is imposed, which is inversely proportional to the riskiness of the assets. So the idea is that the more risky an asset is, the less the maximum leverage that a bank may set should be. So this riskiness of the asset is codified by the volatility of the asset in this case. So how is the leverage connected to systemic risk? Well, this happens because let's say at time t, the bank will set a target leverage that it would like to attain for the next time period, so between t and t+1. And in order to reach that target leverage, it will adopt a strategy. Well, it basically will trade the asset in order to reach that leverage. This is called the leverage targeting strategy. But by doing so, it will induce a positive feedback between the value of the leverage and the value of the prices. This is basically because a large leverage means that the bank will invest more money in the asset, and thus the price of the asset will rise. And this will make the bank perceive the asset as more profitable, and thus it will be led to invest more money in the asset, and it will do so by borrowing money and invest it in the asset, and thus increasing its leverage. So this sets this positive feedback, which if things go bad means that it is possible for prices to crash, and thus for all the banks which are investing in the asset to fail simultaneously, and thus it would mean a high level of systemic risk. So the result of this discussion is that to model the evolution of the riskiness of a given configuration, one should look at the evolution of the leverage of the system. And so this is the main focus of the talk. So in the first, to begin with, one can study the case in which there is only one bank and one asset. This is the case which was investigated in this series of papers. And one can show that one can reduce the evolution of the leverage, so interchange time steps with one can describe this evolution with this map. So there is this deterministic component and this heteroscedastic noise here, which we will forget about in the following. So the idea is to first characterize the deterministic behavior before considering the addition of noise. And this deterministic behavior is described by this map T. So here A and B are real parameters which are not relevant for today. While omega is more relevant. So omega, what does it quantify? Basically, in order to estimate the volatility of the asset which is needed to set the maximum leverage which is attainable, the bank has to look at the previous value of the prices. And it can do so by looking at more into the past or less into the past. So if an omega close to 1 means that the bank has more memory, and thus we will look at more data into the past while performing the estimation of the fluctuations of the prices. While an omega close to 0 means that the bank is more myopic while doing this kind of estimates, and thus it has a smaller memory. So one can study these maps are made like so. So these are unimodal maps. This is for different values of the omega, and one can study the behavior of these maps, and one can see that for small value of omegas, there are some irregular regions where the behavior is chaotic, which is also confirmed by looking at the Lyapunov exponent. And well, one can exploit several results from one-dimensional dynamics to say something about the uniqueness, for example, of the metric attractor of this map, or one can characterize which kind of attractors are possible in this case, and so on. But I mean, these are standard results. For this, for example, we were able to prove that there is a set of positive measures for which the bank has a chaotic behavior, which means that it is topologically transitive and it has a unique absolutely continuous invariant measure. But I mean, one can say something along this line for this map. But this is the starting point for the more general case, which is more relevant for systemic risk, in which one has multiple banks which are investing in a common asset to begin with. So in this case, well, to each bank it is associated a leverage, of course. So one has this set of values to look at. And the evolution of the leverage of the bank I will be described by this map Ti, which is quite similar to the one we had before. The only difference is that now the evolution of the leverage I depends on all the other leverages through this kind of mean field sum. So the idea is that, pi j here represents the size of the bank j in terms of asset owned. The idea is that, large banks will have a greater impact on the prices of the asset. And then this means that indirectly they will also impact the evolution of the leverages of all the other banks, since they are all investing in the same asset. So, of course, each bank may have its own memory. So the idea would be to study how this deterministic system behaves for different choices of omega i's and of the weights pi I. Of course, even in this case, if one traces back to the whole derivation of this, one would have an heteroscedastic noise term on top of this, but we only focus on the deterministic part for this talk. So let's start by studying the simplest case in which one only has two banks and all the two omegas are the same. So we call it the homogeneous case. So in this case, one can see that the two leverages, so lambda 1 and lambda 2, the green one and the blue one, asymptotically synchronized, so they will behave in the same manner. And the common behavior that they will both assume depends on the common value of the omega. So for large omegas, like this is 0.8 and this is 0.3, so decreasing omegas means an increasing of irregularity, which is quite, it's not so surprising if one thinks of the previous bifurcation diagram for the one-dimensional case. And so in this case, one can basically reduce the study of the system to the one-dimensional case, since the only parameters which governs the evolution of the system is the common omega. And indeed, one can actually prove that this synchronization happens for an arbitrary n. So if all the omegas are the same, one has asymptotically the leverages behave in the same manner. And this happens independently of the relative weights of the banks. So it doesn't matter if one bank is much larger than the other. As long as they have the same omegas, they will behave in the same manner. And thus, one can reduce the system to the one-dimensional case, which we talked about before. So in the heterogeneous case, instead, where the two omegas may in principle be different, one can observe that the situation is a little bit more complicated. So in general, there is not a synchronization between the two leverages anymore. But what happens is that the two leverages will have the same qualitative behavior. So if one is periodic of period 4, the other will be periodic of period 4 as well. Or if one is chaotic, the other will be chaotic as well. But which is the qualitative behavior, this qualitative behavior which is shared between the two banks depends in a non-trivial manner both on the relative weights between the two and the two omegas, as is seen here, for example. So one can also look at the evolution of the system in the lambda 1 versus lambda 2 plane, and one sees this kind of fractal attractor. And indeed, one can calculate the estimated box counting dimension, which happens to be non-trivial. And indeed, one can also, it may be not so surprising to see this similarity with the non-attractor if one thinks that one is dealing with a unimodal map, which are somehow perturbed by this mean field perturbation. And if one performs some expansion in certain range of the parameters, one can actually reduce the map to one which is topologically conjugate to a Henon map, where one changes the variables to the sum and the difference, since one is basically rotating the plane by 45 degrees. So what we've done next is to study this system in a special case in which one bank is much larger than the other. This is a quite paradigmatic case for several markets. And so let's say in this case that the second bank is much larger than the first one. One aspect, in this case, the large bank is independent of the small one. So it basically, and indeed, one has that the evolution of the large bank is described by the one-dimensional map T, which doesn't take into account what the small bank does. While the evolution of the first map is described by this law. So basically, at each time step, one applies one of these maps from this family. And the map that one applies depends on the particular value of the leverage of the large bank at that time. So this is basically a skew product system where on the base there is the large bank, which is the driver in a sense, and on the fiber there is the small one, which is the forced bank. So let's also introduce this standard notation where I hat is the space of sequences on the base which are miscible, so like the set of trajectories on the base, and P hat is the invertible extension on this. So this is the shift on this set. And while with this notation we will refer to the repeated iteration of the maps on the fiber. So these are the kinds of maps that one has on the fiber. So they have this is for 3 different values of the value of on the base. So these are made less so. They have an horizontal asymptote for large value of the argument. So in this case, one can prove, for example, that independently of the initial condition, one has that the leverage of the small bank asymptotically reach the same, behave in the same manner. So it doesn't, on the fiber, one has synchronization, in other words. So this means that one has a kind of dynamic fixed point. So there is this value x for which this holds. So basically, there is what one called a random fixed point in case of a random skew product. But so there is this only means that the leverages on the fiber will behave in the same manner. It doesn't matter where they start. And one can also give an explicit expression for this dynamic fixed point, which depends, of course, on the trajectory on the base. So given a trajectory of the large bank, one is able to say where all the leverages on the fiber will synchronize. Well, what would the trajectory on the fiber will be? And this is an analytic expression for this fixed point, and the synchronization on this dynamic fixed point happens exponentially fast. So in other words, one has that the Lyapunov exponent on the fiber is negative. And this is what one would call the random Lyapunov exponent in case of random systems. Something which is also interesting is how one can characterize the behavior of the small bank in terms of the behavior of the large bank. So one can say that if the behavior of the small bank is of the large bank is periodic, then the dynamics of the small bank will be periodic of the same period. While if the dynamics on the base is chaotic, then the dynamics on the fiber will be irregular. And it is not easy to quantify this irregularity, but one can say, for example, that there exists an open set on the fiber in which the dynamics is topologically transitive. So all the open set is explored. Well, the trajectory is dense in this open set. And one can also exploit the ergodicity on the base to give some estimates on the frequency of visits of sets on the fiber. So these results are saying that the behavior of the large banks, describe how the behavior of the large bank impacts the stability of the whole system. So it appears that by only setting the memory of the large bank in the chaotic region, all the dynamics of the whole system will be impacted, and thus the whole system will behave chaotically, for example. So this is also relevant, for example, for policymakers, since they may want to identify what the large banks are and impose on them some restrictions of the possible parameters that they can set.
Sorry, but for having the chaotic situation, you should have some assumption of the fiber.
You mean in this case?
Yeah. I mean, if the base is enough chaotic, it also means that the fiber is not like just rotating.
Yeah, yes. I mean, well, using only well, defining the fiber like so, one can already say that well, if the dynamics on the base it is chaotic, one is able to say well. The thing is that one knows that in the large time scale, well, in the long run, on the fiber they will all behave in the similar manner. So one knows how they all.
Because the fiber is given.
Yes, exactly. So one knows how the behavior of the fiber is made, and thus one is able to characterize this one in terms of what happens on the base. So this is the main thing. Yes. So just to conclude, this is another direction we've been exploring. So this is a further generalization in the more realistic case in which there are multiple assets that all the banks may invest in. So in this case, one has to introduce these numbers xik, which basically xik is the fraction of capital of bank I, which it is investing in asset K. And in this case, one has the evolution of the leverage I is described by this map. So one has a kind of m different mean fields, with each one associated with each different asset. And the idea is that the larger the portfolio overlap between two banks, the larger their connection in a sense. So one can think of this as having multiple channels of communication between two banks, and each channel is associated with a different asset. And thus, the larger the number of assets, the larger number of ways the two banks may communicate in a sense. And so we perform some numerical simulations for this in the case of two banks and two assets. This is the case in which the first bank is much larger than the other one. And we set the distribution of capital of the small bank to be equally, to be 1/2. So the small bank is distributing its capital equally between the two assets. And we studied how the system behaved for different choices of capital distribution of the first bank, so x11. So one can first observe that for for smaller values of omegas, the system behaves more irregularly. And this is not so surprising from previous results. But what is also interesting is that, for example, for a fixed value of omega, like in this plot, the more for x11 close to 1/2, one has more irregular behavior. And this is quite interesting, since one may say that to minimize risk, the best strategy would be to diversify the portfolio as much as possible. But this actually shows that in case in which one considers the interaction between all the banks, this may not be the actual the best strategy, since the more the portfolio is equally diversified, equally balanced, the more irregular the system behaves. So this is quite interesting, and we're currently working on this. Of course, there are many directions one can take from here. For example, it would be interesting to analyze the system of two banks, but in which one cannot use the system to SQ products case. So now there is a feedback even from the small bank to the large bank. And this is not so clear because the interaction in the mean field does not happen as a sum on top of an autonomous map. But I mean, this is something which may be worth looking at. And then there is the whole study of the case in which n is not equal to 2. It would be interesting, for example, to study how a given organization of the weights impacts the stability of the system. And then there is the random system, of course, that I haven't talked about today, which one could study on top of this deterministic skeleton I've mentioned here. And then there is the old multi-asset case, and the connection that one may set between this case and several mechanisms of contagion spreading of networks, which have been explored before in the literature of systemic risk. And that's it. Thank you for attention.
Are there any questions? A short question, maybe? I wish to ask you, who can reach the 18 slide? When you do the definition of chaotic map.
Yes.
In this definition, you use the say that there is a topological transitivity in a subset of interval E.
Yes.
Okay. But which is the invariant set? Is E? Is it the dynamic invariant on the whole set E, or is invariant on the small subinterval? And why you require also the existence of the invariant measure? Is that a definition for your specific problem, this that you use, or there is no other reason? But typically, you must have an invariant set, topological transitivity,
Yes.
sensitivity to initial condition. Why you require topological transitivity? You can have, for instance, a subset of subinterval of E that are disjoint. You can have invariance on each one, but it is not clear to me what you mean. So
Yes, I mean, this is
not technical, but it's, your definition is fitted to your problem, for this specific problem.
No, I mean, this is quite, it's not so restrictive in this case. For this kind of map, one can show actually that one can classify the possible attractors. Like one can say that they either have a periodic attractor or an invariant attractor made of several the finite union of intervals, or maybe a counter set.
But these intervals are disjoint intervals.
Yes, one can describe the attractor as a finite union of the disjoint intervals. And one can say that, if there is a...
If are disjoint is not typical attractor.
No, yes.
Typically, you use topological transitivity to avoid that you have the dynamics on different attractors.
Yes,
we have dense orbit on the attractor.
Yes.
Yes.
But one can say that in this case, for example, the requirement of having an absolutely continuous variant measure in this case is equivalent, to having a positive Lyapunov exponent. So, if one wants to require the sensitivity of an initial condition, that is quite a natural definition to adopt. So, for this kind of class of maps, one can show that this definition is quite intuitively connected with the usual definition of chaos that one can have in mind, so it is quite natural to adopt it, and it is not so restrictive in the it's not specifically designed for this problem.
Okay. Thank you very much.